So we will start off with the notion of a function, and let me first share my screen. So I hope you can see my screen now.
Yes, doctor, we can.
This is the usual story. Yeah. So we will be starting with the notion of a function.
I don't see it yet on my side.
Yeah, me too. I don't see it.
I can see it now.
Yes, I can see it now.
But now I can see it.
Okay. So now it should be seeing everyone. Okay. So as you saw, the notion of a relation is one way of ensuring some kind of a structure, right? Some kind of an arrangement, and moreover, what are you doing? So suppose if you have a relation on a set, from a set A to a set B, we also said that the domain of this relation is A, or people also write this as domain of R. Then I said the codomain of this relation is B. People also write this as this. And we define this range of this relation is the collection of all y in B, such that there exists some x in A to which y is related. Okay? So that's the range. So now, if you look at it, for each x in A, for each x in A, you can have several members. All of these are related. So how do I say? I write it with this squiggle thing, not meaning any kind of a correspondence or any such thing. So there are several y in B which are related to x. And similarly the other side, for each y in B there exists several x in A which are related to it. So in essence what you are doing, so specifying a relation, so if you give me a relation, that's another way of specifying it would be, is to tell for each x in A to give this set, say if I call this to be Rx, give the subset okay. So you see, this automatically brings in what we have already called the indexed set. So we have a whole family of subsets. And in fact, this is both ways. If you give me this so as I said, this is I indicated how to get these Rx's from R. On the other hand, suppose you were given this side, so let me say it in Suppose you gave me this indexed family, then I'll define R to be the set of all those xy's such that y belongs to Rx and x is in A. So that perfectly defines a relation on A cross B. So essentially, the crux of the matter is giving a relation. So the idea is something like this. You had your A and you had your B. To each such thing, you are just going to give me all those things which are related to it. For here also, you are going to give me, there can be overlaps. I don't know why they shouldn't overlap, right? And so on. So you give me all these things, and then what you essentially give me is a relation. And that's one of the reasons why we often say that a relation is many-valued. Now, coming to this idea of many-valued and single-valued. On the other hand, we are now going to see a very special kind of a relation which is not many-valued in this way, but it is single-valued. So what is the idea behind, so what do we get therefore? So the idea therefore, instead of something like this, it tells me it is something like a black box. Something like a black box in which you give an input and you get an unique output. So one input gives you a unique output. On a case of a relation, there would be many over here, but here only one. So single input gives you a single output. So that's what are. That's are what are known as functions. So to put it in a formal way, a function with a function f with domain A and codomain B is a relation. Such that its domain is A. Remember, this means that x belongs to A implies that there exists a y belongs to B with xy in this set F. Okay? And the second one is this unique values. So it says if xy, that's what you are saying, and xy prime, both of them are in A. So if you had both, given the single input x, if you tell me that there are two outputs, it must be that the outputs are same. Okay? So that's the formal definition of a function. So, and then you come back with all those pictures that you have had before, that well, if you can draw a graph of it, that means what is the graph? You're actually plotting you are actually marking those points x and y in the plane which are related by f. And then if you do that and take any line parallel to the y-axis, then it will cut those marked, the locus, that means those marked things on that graph only once. If it cuts twice, it is not a function. Yeah? So you see that actually means that for each you can find at most one y. You'll find a single y. A minute, this is a phone call, I'll give it to my wife. Hello? Hello? Okay, so is this clear now? What do I mean by function and so on? Yeah?
I wanted to ask, Doctor.
Yeah.
Let's go back to the definition of a function.
Yes.
A function f with domain A and codomain B.
Yes.
Is a relation.
Yes.
F is a subset of A times B. My question is on the A times B part. I see in some instances it will be A times A times B. I don't know how we can differentiate the two there.
If it is a subset of A times A, that means it is a function with domain A and codomain A also. Yes. You can have such functions. Say for instance, when you pick up, say you define the function from natural numbers to natural numbers itself, which takes a natural number and just multiplies it by 2. Okay? So x going to, the input is x and the output is 2 times x. So then it is a function from natural numbers to natural numbers. So it is actually a subset of n cross n. So is it clear?
Yeah, I get it.
Okay, I never said though that I was coming to it. I never said though that the codomain and the range are the same things. So if you now rephrase this notion of a range, this thing over here, so the range of f, this is the collection of y in B such that there exists an x in A with xy belongs to f. Now I'll rephrase this after some time. I'll need some good symbols too. So what are some conventions? Let me say a little bit about the conventions, usage and so on. Now if you take an x, given the first coordinate, the second coordinate is, so y is unique, right? For a given x. So once you give me the first coordinate, the second coordinate is unique. And this y is often therefore written as, instead we often write it as fx. So this is nothing else but a restatement of this fact. So that is how we write it. And this we could not do for a general relation because, as I indicated, a single x might be related to several y's. So you cannot do it. But here, this second part of the definition automatically tells you this y is unique the moment you give me an x. So y, it's natural to denote it by something which shows its dependence on x, and why not therefore to write it like this and speak of it as f of x. We often say f of x or image of x under f. You can in fact say the image of f under x. Okay? Given this, the definition of the range becomes very, very simple. It is just the fx's such that x is in A. Okay? And this is obviously, as you know from before, this was a subset of B. Clear? So y equals to fx. You see here this equality is it's rather a denotation rather than saying it is equality in the sense of an assertion. So it is a denotation. We denote this y, that unique y which is related to x by f of x. Okay? Now, there is also another way how we write this. We often write this as or when we write fx, we don't write this f on the top. And this symbol is often reproduced in LaTeX by maps to, and it is called the maps to symbol. So you will read this symbol as f. So x is mapped to y by f, or x is mapped to fx, something like this. Okay, so that's another denotation of this symbol. Also, we will start writing to denote all of this, that f is a relation satisfying 1 and 2 by this symbol, or some such thing like this. Okay? So this is alternative symbolism. By the way, unlike, well, this theory, this is very young. Unlike, and there is a pun over there, I'll explain it. Unlike this set theory, which was possibly, although we have been using sets for a long time, but set theory was first pronounced as a way to think and so on by Cantor, George Cantor, in mid-1600. But, and all of this notion of relation, function, it was in fact done by him. It was in fact done by him, and it was done for a very, very strange reason. He was actually trying to study properties of real numbers, and from there he came up to the question as what do we mean by finite collections and finite sets of real numbers and infinite sets of real numbers. And to give a proper definition of finite and infinite, he came up with this whole bunch of ideas which have been now written as set theory. So, okay. But this symbol which I wrote just now, people used to write for centuries like this. So it's a relation so that to each member X of the domain set A, there is a unique member Y of the codomain set B, and so on. So this definition was written every time when it was used, right? Until as new as, or as very recent as I said, as 1938, while working with differential equations, the name of the mathematician was in fact C.E. Young, who came in, gave this symbolism, this dynamic symbolism, and it took up. Okay, we'll very soon. So, functions kind of give a picture of a transformation, as if you're transforming the elements of the domain into elements of the codomain B. Okay, and properties of these functions is what we are going to study. And the symbolism therefore seems to get set with this idea very well, and we will see how it is, this symbolism itself is going to revolutionize revolutionize in the sense it is going to make things much simpler on what we are going to say henceforth. I would just invite you, just for today, you go back, and for each time when I have used this symbol, you replace this, every time you replace this by this big definition. So, by this big definition that is over here, or the definition of the function, okay, you just replace it by this and see how cumbersome it becomes to express the mathematics and the underlying thought, and how easy it becomes the moment you insert or introduce a symbol. So that's how symbols play a very important role in precise understanding and propagating what we are thinking. Okay. So now let's come back to the mathematics itself. So so now we have come up with the notion of a function. Let's see some examples. Obviously, I'm not going to repeat all those school day examples, so I just write it out. As well as non-examples, so which you have seen in your so far, so like fx equals x squared, x cubed, and so on, and y squared equals to x is not a function, and so on, all those things. Domain, codomain, you can find it out. But here are some more general things, or things. The first thing that comes to my mind is, given any set A, you know this relation, the equality, as I said, on this set A. Now observe, this is a relation with domain A. This is obviously with domain A and codomain A also. Furthermore, given the first coordinate, the second coordinate is uniquely determined. So this is actually a function. And this function is often called the identity function on A. and is strangely written like this. Or many others write also like this. Some people even write it like this. Okay? And what is it doing? It is taking x, and what is it is taking it to x itself. So x is going to x. So 1a of a 1a evaluated at x is x. Okay, so written as a function, it is written like this, 1a. I shall use this symbol 1a. And written as a relation, it is the equality relation, it is delta e. Okay, the same thing. Okay, so that's one relation, one thing which immediately comes up. The next one is, suppose if we have a function this, and we have a function this. Okay? So it means that f is a relation from a to b, and g is a relation from b to c. So we have the composite relation. And what is it? X, z, if and only if there exists a y in b such that x is related by f with y and y is related by g with z. Clear? Any doubts? Hello, am I alone, or can you hear me?
We can hear you, Doc, yeah.
So is it clear?
Yes, it is.
But now observe, this G composed f is also a function. Why? Obviously we can see that the composite, the domain of this relation is A, as we know, all of us know it. But observe, suppose if you tell me x if you tell me also this, then this tells me that there exists a y prime in B such that x f y prime g z prime. But since x f y, the second, and f is a function, and f x f y prime, so this tells me y is equal to y prime. And then you have told me y gz and y gz prime forces z is equal to z prime by the same reason. So z is equal to z prime, and hence G composed f is a function. Okay? So the composite relation of two functions is a function. Okay? And we will often write this diagrammatically. You will see with Young, these diagrams came into being. So we shall often rewrite this as G composed f. We denote it by this, as we denote that relation, and therefore G composed f, if you use that denotation formula, it is G of f of x. G composed f of x is G of f of x. Okay. So that's, and obviously, as you have already shown, that composition is associative. So over here also we don't need to repeat that, but I will repeat it because I will now come to certain things. So you will often see such graphical diagrams. So you see here, okay, let me say, so this is, say, G. I'll often write it also like this to make the graph well decorated, okay, and H. Now you have, this is your G composed F, as well as you have this composite, which is composite of these two, which is your H composed G. Okay, now you see you have two more, so you have this third level. So you have this one, which is H composed G composed F, and you have this other one, which is H composed G composed F, and as relations you know that these two are same. You have already seen this. This is associative. But why I drew all of this is, we will often have such diagrams in which there will, schematically the diagram would look something like this. So there would be certain nodes, okay, certain nodes and certain arrows between them. And so on, okay, possibly something like this. So we will call such a diagram to be commutative if whenever, so such a diagram, the nodes will be sets or objects as we have seen just now. So it will be something like this. The nodes will be sets, and the arrows will denote functions. And if you have a chain of such arrows, we will no more exhibit this composite one. So if we have this F and G, we will no more write this G composed F. We will know this composite, this composite is G composed F, it is there. Okay, that's the first thing. Next thing is, sometimes we will have such, we will say two such things, this diagram commutes. What do I mean? If you take any two nodes, and if there are two paths, we might think of these as denoting some paths. So one path in this diagram is this one, and the other path is this. Okay, so whenever we have two paths, we could have even something, another third one even, say. So let's make it a little more. So we have three paths over here. To say that this diagram commutes means that this central one marked with a tick is the composite of this and this, as well as the composite of this and this. Okay, so that's what it says. So any two paths, so if you have two, to say a commutative diagram, it means any two paths between two nodes are equal, and it actually therefore gives us nothing else but an equality. So if you had an equality between It's an equation involving compositions of functions. Okay, so an equation involving composition of functions will automatically be now alternatively be replaced by such commutative diagrams, and we will call them commutative diagrams. You will see that usage of these diagrams are of great help in the sense that a pattern would seem to emerge from this usage. Okay. All right. Now another function which is very closely related to the identity, but it is not. So suppose if we have a subset A of B, then there is a function, so which we will write as IA, and I is for the inclusion. And what does it do? It does, its rule is same like the identity map. Okay, its rule is like the identity map. So IA of X is actually X, but it is definitely, so the rule agrees with the identity map, but this is not the identity map, because the identity map has both its domain and codomain same. Okay, so here the domain and codomain are different. So therefore these two maps are not the same, and this is called the inclusion map of A in B. Okay, so herein obviously comes in how do we decide two functions are equality of functions. So if we have two functions,
Doctor, I've lost your screen.
Me too.
Okay, let me try and share it again.
It's fine
It's
now.
all right
Thank
now.
you.
Yes, thank you.
Yeah. So if we have two functions, as we know f and g are sets, so coming back they should be equal as sets and so on. So it boils down to say that f is equal to g if and only if their domains are same, their codomains are same, and then for each x in A, which is same as C, fx is equal to gx. Okay, and this exactly falls out from the fact that they must be equal as sets, and if we go on successively using what we have seen, so A cross B must be, it's a subset of A cross B, it's a subset of C cross D, and the domain of F is A, the domain of G is C. So if they are equality, therefore means that the domain of F and domain of G must be same, so A is equal to C. Gone. Then you have, by the same rule, B must be equal to D. Okay, otherwise as sets they are not exactly the same, because it's one is a subset of A cross B and the other is a subset of C cross D, A cross D. So unless B and D are same, it cannot be. And then when you have both A and domain and codomain same, now you only concentrate on the graph, which is xfx and xgx. Those two graphs must be same, and therefore the third condition comes up. So there are three. If any one of them differs, the two functions are different. So by this clue, this identity of this inclusion of A is neither the identity of A nor the identity of B if this is a proper subset. Okay? If A and B are same, they are equal, then obviously identity, this inclusion is nothing else but the identity map. Yeah. Okay? Alright, so we have composites, we have inclusion. What more? Let's see. So here are something called the projection. So remember we had okay, and then we now have two projection maps. They are called product projections. What does it do? It takes this pair, the second projection projects it to y, and this one projects it to the first x, which is the first quadrant. So if you try to make a picture for it, if you have this being the A axis, this is the B axis, then your projection is this, and this is your projection PB. Okay? So it's the projection, so that's why it is often called the projection maps to the axis or whatever. Yeah. So this is there is another now this one 6 is a very interesting number, so let's have an interesting example now. So we were speaking about this. That's what we were speaking about. Now what happens if A is the empty set? Any idea? Well, remember, okay, firstly, look here. This why I always insist that your proofs must not include any English words. It must be very crisp, using just statements and manipulation of those statements. And you might have seen that I have sometimes said refer to the truth table and so on, because it is just a manipulation. We are going to give a meaning to this. Now, why I say so, this is where our words, our words are so very incapable of expressing things which are absolutely logical. That's the whole point of the story. You will say, well, empty set means you have nothing, and you told me function means you're transforming the elements of A into the elements of B. Well, when you have nothing, how can you transform? Well, my answer is yes, exactly, you are right. You cannot do any transformation. So you have the empty map. And this is the part which is taught to me by logic. It is not from the language. Now what? Look into this definition. The definition says, firstly, if you have to write something like this, f is a function from a to b, it must be this. So this is the statement which it must satisfy, the first one. The second one is this, so which means this statement. And the third one is this. Okay? Observe, whenever, from now on, whenever you find a definition, start looking into the key statements. The rest of this, whatever I have written, a function, f, blah, 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 all that is nonsense. The real sense is here, these three marked things. So this is the real sensible thing. That's the first one. This is the second one. And this is the third one. Okay, so first, with everything, now focus your attention on these sensible things. The rest are nonsense. Okay, or you can think of them as decorations, whatever. Now, of these three statements, only this one is an assertive statement. It asserts, it tells you something, it asserts a property. The rest two are implication statements. And whenever you have an implication statement, remember vacuous implication is there. So, you can have instances where this hypothesis part is false and this hypothesis part is false. And so even if that holds good, you know that these two statements will become true. So it is only this assertive statement which you should keep in, which is asserting and telling you something. Okay? If something is defined only via implication, then you know it can go, well, you have no assertion there, it is a implication. Okay? Just like the notion of a transitive relation or a symmetric relation. So empty relation also becomes a transitive and symmetric. But assertive statement tells you, assertion tells you that on a non-empty set, the empty relation cannot be a reflexive relation. Okay? So you see the difference between an assertive and an implication. So now let's come to this again. So, A is empty. So the first thing, F is a subset of empty cross B. And we have already seen that this is the empty set. Clear?
Yes, Doc.
So therefore, F is nothing else but the empty set. Clear? Because the empty set is always a subset of F. Empty set is always a subset of any set, and this tells you that it is a subset of the empty set, so F must be the empty set. Now the second condition. X belongs to the empty set implies there exists a Y in B such that is this statement true?
Yes, it's true.
Yes, it's true. Correct. Because this is false. I don't need to see the other side. Okay, so this is true. Number 3. Suppose x and y prime belongs to the empty set, then y is equal to y prime. Is this true?
Yes, because the position is false.
Which one? Yeah, this first statement, the hypothesis is false. Yes, correct, yes. So this is also true, right? So you see, in this case, vacuously the second and the third conditions are true, and so there is only one candidate which is possible, and that is the empty set. And that's what I said. Yes, you are right, you can do nothing, and so you have the empty function. So from the empty set to any set B, there is one and only one function. This is the only function. Okay? Now, for denotational purposes, so we often, we know it is the empty function, but we often denote it by this symbol. And we will, not IB, but a bold I. So it's not the inclusion, but it is something like the inclusion, because phi is a subset of B, so that's why we call it, say, the IB. Okay, we denote it by IB. All right. So
I'm still worried about the statement, the only function.
Because you said, you started off by saying the case was A is empty, so you wanted to find F from empty to B, and the first condition told you that F cannot be anything else but empty as a set, right? So you have no other choice, no choice. This is describing, this is the assertive part, tells you that F has to be the empty set. Is it clear?
It's clear now.
Okay. Now let's take the other side. What happens when B is empty? So again, the same story. The first one says F is a subset of A cross this, which is this. So F is the empty set. Good. Now let's say X belongs to the empty set implies this empty set, because this is F. There exists a Y in the empty set, because you said B is empty, such that XY belongs to the empty set. Okay? Now, I didn't say anything about, sorry, I made a mistake over here. X belongs to A, because I don't know about A. I said B is empty. So since I said B is empty, so this should be the statement. Okay? So now, can this statement be true? So let me write the third statement. You tell me which statements would be true. XY and XY prime belongs to empty implies Y equals Y prime. So which one of the statements are true? 2 and 3? Remember, this came up because this is same as B. Okay? Which one of these statements are true? 2 and 3.
And both of them true.
2 is false.
Which one?
2 is false. Yes.
2.
Why is 2 false?
Because an empty set cannot contain any
Because
elements.
your B, if your implication, the hypothesis and if your hypothesis is true,
Yes.
but the other side, I'm not sure.
Consequent. The other side is called consequent.
Consequence is false, then it's false.
Correct. So this is false the moment A becomes non-empty.
Yes.
And if A is empty, that is already the first case. Okay? So this is true if and only if A is empty. Okay? Correct? If A is empty, we have already seen it is true. And if A is non-empty, it is not true. So it's false. Right? As you said.
Yes.
Okay. Number 3. Number 3, is it true or false?
It's true, because the
Yes.
hypothesis is false.
Correct. So it's true. So what we conclude? So if the codomain is empty, there can be a function if and only if the domain is empty. So that means it tells me if the domain is non-empty, then there exists no function f from A to the empty set. So you cannot transform a non-empty set to the empty set, but you can transform the empty set to a non-empty set. Okay? All right? It's already 7:30. We should stop. But just let me introduce a few symbols, denotations. I like this symbol, and we will see why I use this symbol pretty often, and I like it. This is nothing else but the set of all functions. F whose domain is X and codomain is Y. Okay? There is an alternative symbol for this. People often use this symbol also. Y to the power X is also used. But I usually like this symbol. So, and there is a reason why I like it. And you will see very soon when we when we do a little more mathematics that this is becoming very common. So that's why I like it. So what we have done so far is, but we have therefore said for any set Y, this set has a single element. And this set, we have completely described it, and we have said that we will denote that single set by bold I, Y. We know that this is nothing else but the empty set. As a set, this This I, bold IY is the empty set. We know that. And we have also shown that X, this set, the other way around, this is empty if X is non-empty. Okay? So that's what we have shown so far. And if we come to our notes, it's section 5. You will see that there is another in 5.4. I have put up another interesting view of a function, which is the stock diagram for a function, and then you will see several these examples I have discussed, and there are many other examples, and there are several things written in red. Okay, so that would be the next next week's exercise. So up to section 5.1, that's the exercise. Okay, next
Just a question, Doc.
Yeah.
Did you already share the document for chapter 2?
No, this is section 5 of chapter 1. I'm still writing the whole thing. I'll put up another version of this, the recent version today. I'll put it up so that it matches with what I'm saying. Okay?
Oh, okay.
And you will see many more things that have been written, and they will go on changing and so on. So, as I said, I'm still writing this. Now, so firstly, for the next week, it will be section 5. Okay, up to 5.1. Okay, up to 5.1. That would be our next week's material with which you should be prepared. And it would be nice if you have a reading of 5.1 so that it would be clearer next time. That's the first thing. The next thing is regarding your submissions. What I thought was, so suppose, say, let's go back to what we have. Say, for instance, in this section on equivalence relations or symmetric relations or equivalence relations and so on. And let me try to find out some questions which was there. Equivalence relations possibly was just written, and only in the end there was one question I seem to remember. Oh, here, the opposite relation. Say the phrase the opposite relation works for relation between employees and division. So things which are written in red and you're asked to evaluate, those are your assignment questions, right? So when you are answering this, you can say this as point, this as, say, find out a possible way. But what I wanted to say is this thing in red. You might even write this as your assignment question. Phrase the opposite relation works for relation. Each such will which will be evaluated to 5 marks, and so each section that I am saying will have a total number of points, and you can have those who have submitted already. I have sent my feedback. I'll give these marks and send those feedbacks again. it doesn't mean that you cannot resubmit. That's the first thing. So even after you send it for the first time and I give some feedback and you resubmit, you can do that, and that will only better your marks. Okay. So for each section there is certain total number of points depending on how many Y's and so on and so forth are there. Each is 5 points and you will get as much as you can score over there. And that's the assessment thing. So are you agreeable on this kind of an assessment, right? So it is going to be continuous, week by week. Each question asked over here will have 5 points. You will be evaluated on 5 points. Okay? Clear? And you can have multiple submissions for the same thing so that you can make it better. Alright? Am I alone?
Alright.
Yes,
Yes,
Doctor.
We can hear you, Doctor.
Okay. So
But Doc, sometimes it's difficult to know from a section which ones are questions, which ones are not.
sometimes it is declared very, very clearly. So, for instance, yes, at least from section 5 onwards, you will have very clear. So, yes, you're right. Initially, I don't see a lot of them. But from section 5 onwards, I was very, very clear. You will see something like this in things written in red like this. Why? Explain. In brackets. Written like this. Or directly said, write down the proof of this completely. Do this completely. This said from section 5, I was very clear. Before that, I was not that much clear, it seems, yes. But from section 5 onwards, you will see it is getting very, very clear and very crisp. I was also not crisp.
Okay, thanks.
Just to add on to that, Doc,
Yes?
what I did was, you'll see that the previous sections, there are many sections where it says proof left as exercise.
Yes.
So where it says that, then I took it as an exercise. And for others, for example, theorem 4.2, you did 2 examples.
Yes.
So I took the rest are exercise except for those 2 examples.
Yes.
So that is how I tackled it.
Good.
So
yes.
I only left those which you did as examples and did the rest.
Correct. So, yes. So over here I will do accordingly as you said. But for the rest it will be very clear. From the notes itself you will understand which one I am asking you to prove. That's the first thing. So you're now clear on the assessment side. How will it be assessed and so on, right?
So it will still be 20 marks. Or
Each such question,
cumulative.
each such thing like this, why, explain or prove and so on, would be 5 points. So
I mean the overall on this.
Yes. So finally what you get, so you see, finally these 2 assignments together would constitute 20% of the, would contribute 20% to your final mark. So your year mark is, so this, as these assignments constitute of something called the year mark, and your examination would constitute what is called the exam mark. 80% of the exam mark will be taken and 20% of the year mark will be taken as the final score. Okay? Is it clear?
Yes, Doc.
That is.
Okay. So that's the first part. Now regarding submissions, as I already said, PDF and so on. Now when you submit, because you see I have to select them from hosts of email that come to me. So let's make a convention. So if I were to submit, my file name would look like this. So this is my first name. So you just put your first name, a dash, your student number, right? The date, say if you are submitting it today. Okay. So first name, so your file name should look like this. And the date exactly as this. So days, months, century year dot pdf. Okay, so that will help me to search by your first name or your student number from my emails, your submissions. Otherwise, it gets a little bit. You see, I have a whole lot of emails. From there, it might get lost. So that's why
I sent the first part last week, Wednesday, Doc. I don't know if you saw it.
Yeah, this last week I was
Wednesday, and then today, and I sent the second part.
Okay, so you sent me two. When I write back tonight, you will see. And if you have something more, you can resubmit. Send me again. But I will go through all your submissions by tonight, and by tomorrow I should be able to send you all the assessments and so on by tomorrow. So let me see. Because last week I was busy. Firstly, I went out. I was not here for a couple of days, and then I was very busy with other work, and so I couldn't check anything. So I don't know. In fact, after last week, it is tonight that I am sitting with you on my machine. So I'll have to check. So let's put your things like this. Your file names should come like this. Okay. And by tomorrow you would be getting whatever you have submitted and your assessment up to that point. You'll be getting that, so you know whether I have missed something or not. Okay.
Okay, thank you.
So I stopped recording.